Alrighty. All right, everybody ready? That sounds like a yes. Okay, so, all right. I'm Richard Steenbergen from GTT, previously NLayer, and today we're going to talk about optical networking. So the purpose of this talk, why do we want to talk about optical networking? Basically, as an industry, a lot of guys spend a lot of time dealing with optical, but not many router jockeys out there actually have enough exposure to it. There's tons of people that know how to move traffic. They don't know anything about what happens when they plug in their fiber. It leads to a wide variety of issues, confusion out there. So the purpose of this talk is just to try and get everyone familiar with every little thing. It's not going to make you an optical engineer. Can you hear? Okay, it sounds like it's doing something up here. Yes. Sound? Is it better now?
We don't hear anything.
Okay. Testing. Ah, there we go. Okay, better? All right. So this talk will probably not make you an optical engineer, but the point is to get everyone familiar with just the basic concepts. Everything from theoretical to practical, from really useful to really mundane stuff. The goal is just to give everyone just a really basic understanding and talk about a little bit of everything. So first off, the basics. How does optical fiber actually work? So optical fiber, obviously, is a very thin strand of glass which just acts as a waveguide over distances for light. Keeps it in, whatever. Guides the waves. What do you want? So it works on a principle called total internal reflection. And that means when light tries to pass between two different media, so in this example, air to water, you've seen if you've been underwater or you've looked through water, you've seen that light bends. At certain angles it bends, and at certain angles it will actually reflect back in at the same angle that it entered. So you see in this example that if you are past a certain critical angle, it bounces back in. That's how fiber works. So fiber is actually composed of two different layers of glass. The core, which is what actually carries the actual signal, and then the cladding, which is a different type of glass around the outside of the core, and that causes the reflection back in. So you have what's called refractive index, which is just a measure of how quickly light passes through the fiber. So the cladding has a lower refractive index, and that causes the total internal reflection inside. So here's a gratuitous pretty picture from Wikipedia showing someone shining a laser pointer into a piece of plastic or something, and you can see that it just bounces around inside and keeps propagating forward. So the inside of a single mode fiber cable, you've got your core, which is 9 microns. You've got your cladding, which is usually 125 microns. You've got a buffer, which is just a coating around the fiber to keep it from being damaged. And then inside of that, you'll have strain relief members. You'll have possibly multiple fibers. And then you'll have the big jacket around it, which is what keeps it from actually being damaged. And what do we actually transmit over the fiber? Well, we encode digital signals into analog pulses of light. Essentially, you're just modulating using a technique called non-return to zero. So it's not quite on-off, but it's a very simple modulation, really fast. And obviously, most fibers work in duplex pairs. If you've ever worked with any fiber, typically what you'll do is use one to transmit and one to receive, so opposite directions. But you can actually send it over one strand. We'll talk about that later. So the basic fibers, basic types and uses. Two main types, single mode fiber and multi-mode fiber. The difference is really the size of the core. So multi-mode has a much wider core, not quite 10x, but much significantly wider, so that multiple modes, basically a mode of light is light, whether it will follow the same transmission path or not. So if you have a core that is small enough it will only allow one mode of light. It will only propagate in one way. If you have a big enough core, it will obviously multi-mode. That's the name. So SMF, 9 microns, and there's advantages and disadvantages to each one. So multi-mode is specifically designed to be used with cheap light sources. So you have a really wide core that lets you send an incoherent signal. You don't have to buy as nice, expensive of an optic. So you can use LEDs, you can use VC VCSELs, which are vertical cavity surface emitting lasers. You can use cheaper stuff, and you don't have to have as tight of a tolerance for any of your connections. So it just makes things cheaper. Basically, what you're paying for by making it cheaper is you no longer have long reach. What happens is you get multiple modes of light in the fiber, and you get distortion. So I'll talk about that in a minute. But basically, you're looking at distances anywhere between 20 to at max 500 meters, depending on the type of signal and the exact type of fiber. There's also recently a laser optimized multimode, which uses aqua-colored cables, and that's designed to let you do 10 gigs up to 300 meters. Before you had that, you might do 10 gigs on multimode to 20 meters or something along those lines. Single mode fiber is what you use in any type of long reach application. So the core is small enough that you can only have one mode of light inside it, and that lets you get several thousand kilometers without completely regenerating the signal. Obviously, you still have to amplify and dispersion compensation, things that we'll talk about later, but you can actually get really long distances with single mode. But obviously it's more expensive. You need tighter tolerances, you need lasers that are specifically aimed, things like that. So classic single mode fiber is called SMF28, which you'll hear a lot. That's actually a product name from Corning, but it's become kind of the de facto standard for classic single mode fiber. There's actually a bunch of other types out there. There's low water peak fiber, there's dispersion shifted fiber, there's non-zero dispersion shifted fiber, there's things that we'll talk about in a bit, but single mode classically, the original stuff was SMF28. There's a bunch of standardized color codes that you will use when working with fiber. So orange is going to be like the jacket on the actual fiber. Orange is going to be your basic 62.5 or 50 micron multi-mode fiber. Yellow is going to be your standard single mode fiber. Aqua is going to be your 10 gig optimized multi-mode, and it's rare, but sometimes you'll see it. Blue is polarization maintaining single mode fiber. We'll talk about more later. So here's kind of a little diagram showing what happens inside the fiber when the core is so wide in multimode. And even inside of multimode, there's two different types of fiber. There's what's called step index and graded index. It's not really important to talk about that, but you can see that there's different types of reflections that happen inside, whereas the single mode, because it's narrow enough that it can only propagate one mode, it just goes straight. There's only one path the light can travel. So big question that lots of people ask is what happens when you mix fiber types? So if you take a optic that's meant for multimode fiber and you plug it to a single mode fiber, what happens? You've got a really wide signal that's now hitting a really narrow core. You're going to lose most of your light. You're just going to go a couple of feet. You're going to lose all your attenuation, your light's gone. You're not really going to be able to do anything with it. If you take an SMF optic, which is a very narrow signal, and you put it into multimode, it'll work, but it'll start to bounce around inside the fiber, and that's going to limit you by distance. But you can actually take something that's designed for single mode, put it into multimode, and you will get the exact same distance that you would have gotten if it was a multimode signal. And then there's a special type of cable called a mode conditioning cable, which is basically just a precise fusion splice between single mode and multimode that lets you get a little bit better distance, so it kind of sets the angle right and aims a little bit better. You'll typically see this in older stuff where you're trying to get maximum distance out of a multimode fiber plant somewhere, but that's what happens. It bounces around in there. So talking about fiber optic transceivers, basically we've talked about this before. There's two links to presentations. There was a 1 gig presentation. There was a 10 gig presentation a few years ago that I did. Basically the latest and greatest updates, looking at it 5 years later. SFP Plus is now common. There are long-reach optics that didn't exist before, so you can very easily do your 10 and 40 kilometer reach optics. You've got lots of 100 gig tuned DWDM out there. 80 kilometer systems are out there in some way. Some vendors are shipping them. Some vendors are not quite shipping them. There's definitely some minor nagging questions on heat and power draw and things like that. But give it a little bit more time, you'll see 80s be very common. SFP Plus is definitely the format of choice for anything enterprise, anything high density, anything the top of rack type stuff. But XFP is still the winner if you want to do anything fancy. So if you want to do very narrow DWDM channels, if you want to do very long reach systems, integrate FEC, any things, and we'll talk about a lot of this stuff later, but it's still where you have to go if you want the good stuff. So now we get into just optical networking terms and concepts. So first off, we talk about optical power. What is optical power? It's just the brightness, the intensity of the light. So obviously as light travels through the fiber, you're going to lose some of it. It's either going to be absorbed by the glass particles or scattered. Physics, you're going to lose intensity, and it's going to turn into heat as it hits particles. The loss of intensity over distance is called attenuation. So what we measure that in is decibels, the same as sound. And a decibel is 1/10 of a bell. It's a logarithmic scale unit that expresses the relationship between two values. That means it doesn't actually measure anything on its own. You have to measure relative to something. All it does is compare two values. So, for example, 0 dB is no change. 3 dB is double. Minus 3 dB is half. Plus 10 dB is 100x. It's a logarithmic scale. So in optical networking, if you want to talk about an actual value, you have to compare it to something, and that's called a dBm, which is decibels relative to 1 milliwatt. So 0 dBm would be 1 milliwatt, 3 dBm would be 2, minus 3 would be half, same concept. So if you completely lose your signal, you are negative infinity dBm. That's how you actually measure it. But it's actually very common for people to confuse dB and dBm, especially if they're out there working with a light meter. They'll put it in a relative mode that's designed to look at testing off a test set somewhere, and they'll get a completely wrong value. So you have to understand there's two ways to measure it. One is an actual value relative to something, so you can say there's this much light, and one is this much change of light, so loss over distance, things like that. So why would we want to measure it in decibels? Because light, just like sound, follows what's called the inverse square law. So that means that over distance, the loss is proportionally squared. So for example, if you travel distance x, you're going to lose half your intensity. You travel distance x again, you're going to lose another half. So at 2x, you're down to 25%. It's a logarithmic scale. At 3x, you're down to 12.5%. So using decibels basically cancels this out. It lets us do simple math when we're working with it. So you can say a 3 dB change every time, and for every unit x, you can say, well, another 3 dB, 3, 6, 9. You don't have to do logarithmic math. That's basically the point. So I threw in a little table that just kind of shows the dB and what it actually is. So you can see you get to what is that, 50 dB, and you get to 1/100,000th of the original power. It doesn't take much towards the end there to have absolutely no signal at all. Another concept that we talk about is called dispersion. So dispersion just means to spread out, and what happens in optical networking is that will degrade your signal. There's basically two types of dispersion that we care about dealing with. One is chromatic dispersion, and that just means different frequencies of light will travel at different speeds through a non-vacuum. So even a signal that is very optimized to be one specific frequency, it still has a high point and a low point. And over distance, that will cause it to spread out, and then you end up with a smeared signal that you can't read. And the other one that's less of a deal, but still out there, is called polarization mode dispersion. And that's caused by the fiber not being perfectly cylindrical, imperfections in the fiber, just moving it around. You're going to have, if you know polarization of light, sunglasses where you turn it one way or the other and you're seeing half the signal, you're going to have one type of polarization traveling faster than another if the fiber is not perfectly shaped. And what this causes is you get a smeared out signal, and now you're sitting on the receiver side, you can't actually figure out what it is. There's a couple of transmission bands that we talk about actually sending signals into. The first one is called the first window, 850 nanometer. Today we really only use that for very short reach stuff, lots of multi-mode typically. But that was the very first window that people figured out how to actually use to send signal over. The next one was the 1310 window. And it was the point of zero dispersion on classic single mode fiber. But it has pretty high attenuation. So today we typically use that for medium reach stuff. And then the third window is called the C band, which stands for conventional band. It covers 1525 to 1565 nanometers. That has the lowest rate of attenuation, so if you're trying to get long distances, that's the one that you want to use. And it has another benefit in that you can amplify it with what's called an EDFA, an erbium-doped fiber amplifier, which we'll talk about later. But the very specific properties of physics that allow this one specific frequency of light to be amplified is another reason that we use it. And then there's a fourth band out there that's relatively uncommon, except for things like undersea systems and things like that, called the L band, and that's just up in higher frequencies. So here's kind of a little chart showing why the frequencies exist. What you see here is the loss relative to the wavelengths. What happens is there's molecules of water that get trapped in the glass, and water absorbs light at certain frequencies. So you can see there's these big peaks where the signal is completely unusable. That's called the water peak. So the original fiber, a lot of fiber that was deployed early, has these huge areas that are completely unusable. And obviously, it's gotten a little bit better over time. Now you see modern fiber is not nearly as bad, but there's still these areas that you don't want to use because you're going to lose a lot more signal at certain frequencies. There's a technique called forward error correction. What this does is it adds a little bit of extra information in the transmission so the receiver can recover from small errors. Basically, you can think of it like RAID 5 for your wavelengths. So, for example, you might take a 10 gig signal, a 10.325 gig signal, which is what a 10 gig Ethernet is, and you turn it into an 11 gig signal. You put just a little bit more overhead on it, but now you've got a lot more protection against loss. You can recover from errors. And that's implemented using something called G709, which is a digital wrapper. We'll talk about a little bit more in a bit. But the benefits are you can take what would be your loss over losing signal and recover from it much better. So it lets you get really long distances. You might take what was previously an 80-kilometer optically and turn it into a 120-kilometer just by adding a little bit of software to it. There's a technique out there called digital wrappers, G709. It's also called OTN, which stands for Optical Transport Network. Basically, it's a set of protocols that let you work with wavelengths generically. So you can go between vendors and not have to. If you ever bought a wavelength 5-10 years ago, you had a problem where everything had to come back to Sonnet, and then that you needed Sonnet in order to work with anything. So OTN lets you take any signal and still work with it. So now I can go to a carrier, get a 10 gig Ethernet wave, and not be dependent on Ethernet's crappy troubleshooting abilities. They can actually troubleshoot it in their network by looking at it as OTN. So it's just a technique that a lot of people use. Now we talk about wave division multiplexing. So wave division multiplexing, WDM, we know that light comes in lots of different colors. What you can do is take all those different colors and put them down one strand and have them not interfere with each other. You get ships in the night. So you have a unit called a mux that takes any number of wavelengths, and you end up with just carrying all of the signal on the same fiber, completely independent of each other. So there's a bunch of different types out there. The most common are dense and coarse. So here's kind of an example of the different channel spacings out there, how wide they are relative to anything. So that's a CWDM channel, the huge one, which is very wide. And then you've got a bunch of smaller ones. So that's a 200 gigahertz. That's a relatively old technology, DWDM. Modern stuff is usually half that or even less. And there's more examples of it later. So CWDM is basically used to mean anything that's not DWDM. There's a popular version of it, which is 8 channels, like 1470, 1490, 1510, things like that. If you've got low water peak fiber, you can get more. You can get into 18 channels of lower end stuff. You can also use it to mean just a 1310, 1550 splitter. You can take those two very common signals, put them on the same fiber, and have them not interfere with each other. Sometimes it's called GWDM, ghetto wave division multiplexing. So DWDM is a much more tightly packed system. That's what you're going to see in any type of commercial long-haul system. You're going to see that based around the C-band, obviously, for distance. And it uses what's called a standardized ITU grid. So that when you say channel 37, you know that your channel 37 is someone else's 37, or they're going to talk to each other. There's a bunch of different grids out there depending on the spacing. So your 200 gigahertz stuff, that was what you were seeing around 2000 era. These days, you're not going to see anything less than 100 gigahertz, which will give you 40 channels in the C-band. Most commercial systems at this point are going to be in the 25. Anything that was deployed a few years ago might be in the 50. But depending on how much money you're paying, you're going to be in the 25s right now. So that can give you 160 channels in the C-band on one piece of fiber. The advantages, obviously, CWDM, it's cheaper. You need less precise lasers. You don't have to worry about the signal wandering. What actually happens is not that the signal itself is any wider, it's that it's free to move about. You don't have to have as precisely manufactured lasers. You don't have to have the cooling be quite as nice. You've got a pretty big window that you can send your signal in. DWDM, you get a lot more channels, but you've got to deal with all those things. And by staying completely in the C-band, you're going to get the lowest attenuation, so you're going to get the best distances, and you're going to be able to amplify the signal, which is any type of real network. You're going to be building something like that. So here's a relative size comparison of the different channels. So that's the CWDM channel is the whole thing, and then there's a 200 to 100 and a 50 gigahertz that show you how many channels you can kind of put in one thing. There's a bunch of other places where WDM is used, non-standard stuff. So for example, there's a type of optic for 10 gig called the LX4. What this does is take 4 non-standard channels and put them over the same fiber. So you might have a 10 gig pluggable like a Zenpack, and what it's actually doing is sending 4 different 2.5 gig waves across the fiber. That lets you get longer distances over multi-mode. It had some advantages for certain technology like Zenpack, which actually talks to the router talks to the optical via four lanes anyway, so it's really easy for the box to take those 4 things, turn it into 4 different signals, put it in a little tiny mux that's actually integrated into the pluggable. These days you're going to start to see that for 100 gig. 100 gig optical, pure optical, just doesn't exist, or it exists in the lab. It's not practical. You can't do any distance with it. So what you see out there is a lot of 4x25 or 10x10, things like that. And obviously you can use it for 1310, 1550, simple muxes, just 2 channels. There's a lot of people that make optics that integrate this. So what happens is you have an optic and it only has a plug for one thing. What it's doing is it's got a really tiny mux integrated into the optic that lets you send and receive over 2 different colors of light on one strand. So for someone who knows nothing about optical networking, they can just buy this one SFP, plug it into their router, and just take one strand of their fiber and then use the other one for something else. Just instant doubling of capacity. So now we talk about a bunch of optical networking components. First off, for WDM, you've got the mux and the demux, short for multiplexer. Some people call it a prism. You can kind of think of it like that. That's not how it actually works. I'll talk about how it actually works, but you can think of it as a prism where you send one piece of light in and it splits it out into a lot of different colors. It's a very simple device. Typically what you'll see is one common port and a whole bunch of individual channels. It's completely passive. It doesn't require any power. If you're working with a commercial system where you don't see any of this, the exact same component exists inside that system. They just hide it. They put it on a card that powers up so you can feel good about it, but it's a completely passive system and doesn't do anything other than split the light. Most muxes, you're going to see a duplicate. You're going to see the exact same thing twice for transmit and receive. Most modern stuff, it's actually the exact same thing. It can work in either direction. So you just put it into one unit. The next thing is called an OADM, an optical add-drop multiplexer. What this lets you do is pass some channels through while dropping others. So you might have fiber going across, and you might have this device here, and you say you want to pass 30 channels unmolested right through, but you want to drop 10 that you want to actually work with. So be able to talk to the A side, talk to the B side. You could do this with a mux, and you would just have to sit there, take 2 muxes, and just do a bunch of short patch cables, and that would be silly. So by doing this, you get a lot less loss, and you can just for convenience factor. So talk about everything there. There's a modern device called a ROADM, which is a reconfigurable OADM. Basically what this is something that you can log into the device and reconfigure what channels you drop. And you can even do fancy things like multi-degree. You don't have to have only one side out and this side out. You could have 3 different directions that you can add and drop stuff. So it lets you design really complex optical technologies, star topologies and things purely at an optical layer. They're relatively expensive. Optical amplifiers let you increase the intensity of the signal. There's a bunch of different types. It depends on the frequencies of light. Different physics are required. The most common thing that most people deal with is an EDFA, an erbium-doped fiber amplifier. What that means is a piece of fiber that's doped with erbium, and you can, by injecting a laser of a completely different frequency, cause the stimulation of light, and these other frequencies, you can make the light get brighter. So you have a pump laser across this fiber, and it causes the light to get excited and amplify. You have optical switches, which lets you do purely optical interconnection without converting from optical to electrical back to optical. So basically, you've just got a little tiny array of mirrors. You've got these microscopic mirrors that are controlled by software. So you can say, link these 2 ports together, and if you want to change it, you can aim it to another port. You'll see these used for optical protection systems, for optical cross-connect systems. They're relatively expensive, but they're really nice. You can have things where if you detect the signal drops, you can just instantly switch which port you talk to. You can change to a different fiber, and probably do it so fast that the protocols don't even know anything happened. Basically, these are used inside of ROADMs to implement those. Sometimes called a WSS, a wavelength selectable switch. So how does a MUX and an OADM actually work? You have what's called an optical bandpass filter. There's these different types of filters, but what happens is there will be a filter that reflects a certain frequency and passes another frequency. So you send to a Bragg grading filter, you send the signal, and it's going to pass through most of it and reflect back another part of it. And use that in combination with what's called a circulator. You probably never run across a circulator outside of building a DWDM system, but that's how muxes are made. So what it does is it's a 3-port system, and when something goes in one port, when it goes in port 1, it comes out port 2. When it goes in port 2, it goes out port 3. So it lets you kind of get a double pass at things. So here you see 2 circulators paired up with a Bragg grading filter, and that's how you actually implement an OADM. You'll also see it used for dispersion compensation. It lets you take the same piece of fiber and run the signal over it twice. There's splitters and optical taps. So optical splitters do exactly what they sound like they do. They split the signal. There's a bunch of common things, but the most common ones are just like a 50-50 splitter. One area where you might see that used is if you've got very simple optical protection. Say you've got two diverse dark fibers and you want to be able to use both of them, but you don't want to actually pay all the investment necessary to fully light these things both ways. What you can do is split the signal in half, send it down both, and then on the other side you've got a device that purely looks at optical receive level, and if it loses the light because of a fiber cut or something, it switches to receiving the other one. So for a 3 dB hit, you've now got instant protection. You can use a very cheap system to protect hundreds, thousands of channels, potentially millions of dollars worth of stuff very simply. Another common use is a 99-1 splitter, which you'll see for optical performance monitoring. So basically you're just going to pull out 1% of the signal and send it over to a monitor, and now this thing can, by knowing that it's 1%, it multiplies by 100, and it knows what's going over this fiber, what's happening on all the different frequencies. So there's actually a bunch of different types of single mode optical fiber that we talk about. So we already discussed that single mode is used for anything that's long reach, but all the different types out there. You've got your standard SMF, your classic SMF, which is called SMF28. You've got your low water peak fiber, dispersion shifted fiber, low loss fiber, non-zero dispersion shifted fiber, bend insensitive fiber, and we'll talk about a lot of these. So your standard classic SMF, like I said, is actually a product name for Corning. It was actually optimized for 1310 because that's where the lowest rate of dispersion, dispersion occurs. So the attenuation is lower at 1550, but if for original systems that were very concerned about dispersion, that didn't know how to deal with it, that was the driving issue. Low water peak fiber is modern fiber that's been designed to reduce the water molecules that get into the fiber. So you see that we were talking about before, that water peak where you had a spectrum that was completely unusable. Now you can start to use it again. Dispersion shifted fiber was an attempt to improve the dispersion at 1550 because that's where the longest reach is capable. So what happens is the rate at which chromatic dispersion occurs changes for different frequencies of light. And if you specially engineer the fiber a certain way, you can shift the point where that occurs to be centered around 1550. It turned out this was actually a really bad thing. People didn't know this at the time, but when you started running DWDM over just straight dispersion shifted fiber, when you hit the non-dispersion point, you started causing a bunch of nonlinear interactions. What would happen is you would take three wavelengths that are supposed to be ships in the night not talking to each other, and they would interact with each other and produce a fourth phantom wavelength. A bunch of physics that's way over my head, but it just turned out to be a huge hassle. So everyone backed away from this very quickly and moved to something called non-zero dispersion shifted fiber. So you're still shifting to get lower dispersion, but you're putting it just outside the signal you're actually using. You're not actually going to use this point that causes all these nonlinear interactions. And what you end up doing is you engineer the fiber in two ways. One, your normal transmission fiber, it will disperse in a certain way, and then they engineer certain types of fiber that will actually disperse the other direction, and you use that, I'll talk about this later, for dispersion compensation. So after you've transmitted 80 kilometers over the real fiber, then you take it and you run it through a spool and you kind of compress it back the other way, so you restore your signal. The other fiber types out there, you've got your low attenuation fiber at the expense of dispersion, so you'll see those in undersea systems and things where you really care about attenuation. You've got your bend insensitive fiber. It's stuff you use in office buildings and things where people can play with the fiber and not break it. It's not as good for transmitting, but it's, you can actually play with it. Modern fibers, usually like the specs that we're talking about here, the modern fibers that you can actually go out and buy right now, they're very good. But you just got to remember that a lot of what's in the ground is old stuff, so you have to know what you're working with. So here's some examples of different types of fibers and kind of how the dispersion and their slopes. Classic SMF standards called G652, and then you've got three different types of very common stuff. You'll find a lot of true wave, leaf, and Terralite fiber out there from Corning and various people. And you see they have different slopes of dispersion. So now we talk about how you actually engineer an optical network. So first off, you have insertion loss. Even the best connectors and splices aren't perfect. Every time you plug two fibers together, you're not getting a perfect alignment. You're going to get some loss. Typical budgetary figure is somewhere around half a dB for a connector, but it actually depends entirely on the type of connector and whatnot. And the phrase insertion loss is also used when you connect to a MUX. It's basically the penalty that you pay just for inserting the fiber. You're paying something. Real life example, if you plug it into a 16-channel DWDM system, you're going to see maybe 7 dB of loss going through this DWDM, just going through internally all the components that it uses. And here you can see 3 different types of insertion losses that you see when connecting cables. One, mismatched core size, which we talked about before, but it can actually happen in between even single mode fiber. Some fibers will be 8 microns, some will be 9. If there's any type of difference, you'll have mismatched cores. You can have misaligned cores where the things don't quite meet up perfectly, and you can have an air gap between the fibers. Just you don't fully insert the fiber. It'll still work, but you've got that air in the middle, and it'll start to lose a lot of signal. So when you're building an optical network, you need to have an optical budget. Basically, when you look at something and it says 40 kilometers, that doesn't really mean anything. That's a guideline. You can either do much better or much worse depending on what you actually do with the fiber. And it's smart to leave some margin in. What's going to happen over time, say there's a fiber cut and then someone comes along and fixes it, now you've added a new splice. Say someone starts moving patch cables around, someone's up in a cable tray and starts shifting your fiber. There's all kinds of things that happen in real life that change the signal. Even over time, the transmitters will actually start to cool off. You'll start to send less and less signal as they age. So what started out as a really high margin system might go down over time. But here's just kind of a little diagram showing fiber loss over distance, the connector losses, the splice loss, and you're trying to do a little planning and make sure that you stay within that budget. Here's just a table of some of the common types of losses. Typically, the real loss is a lot better than the worst case loss, but it can happen. Factory-made connectors, field connectors, fusion splice connectors are going to have different things. If you, for example, you're out at a colo like an Equinix, and they terminate a fiber for you, what they're doing is a field terminated connector, and so that's going to have some loss on it compared to buying a perfect pre-made patch cable out of factory where it's being done with a machine that's going to do it perfectly. You're going to see different rates of loss at different frequencies. So here's kind of just a little table that you can look at. You can see that there's obviously a lot more loss at 1310 than at 1550, and what's called dB over kilometers. When you're actually working with amplifiers, you need to balance the power. So when you're working with amplifiers, the gain is not always consistent across all wavelengths. You might have one portion of the spectrum that is amplified more than another, and there's a bunch of consequences that happen if you don't take care of this. You cause a lot of signal noise issues. What happens is the total power in the system can only be so much. The amplifier can only do so much, and so when you've got 10 channels and now you add 5 more channels, that changes the amplification that happens to each individual channel, and you need to flatten this out, so you'll have a lot of gain flattening amplifiers. This is what I was talking about. They have limits on the total power that they can put into the system. So just think a single DWDM channel at 10 dB is only 1 milliwatt, but you put 40 channels in there, you've now got 4 milliwatts. So that's going to affect how much you can actually amplify each channel. And you've got to remember that this will change over time. So for example, if you just have a standard dumb amplifier that's passing 40 signals and all of a sudden you lose power in a rack and 20 of these signals drop off, it's going to change instantly the total power in the system. So you need a good EDFA that can actually look at what you're trying to achieve and kind of adjust the gain dynamically. To deal with dispersion, you have a dispersion compensation unit, which is basically just a big spool of fiber with the slope in the opposite direction. So like I said, you run it 80 kilometers over transmission fiber, and then you run it through one of these spools, and you kind of shift it back together the other direction. And you might throw a circulator in there too, so you get double the use over the same fiber. Modern stuff is actually doing a lot with electronic dispersion compensation. That's basically what allows a lot of 10 gig technology right now and 40 gig, things like that. You're doing a lot of electronic compensation. One thing to keep in mind is that in the SFP Plus spec, this was actually moved out. It used to be, in an XFP, the electronic dispersion compensation happens on the optic. And so you can go out many years after you buy your router and go buy whatever the current state-of-the-art pluggable is and have it be able to do maximum distance. If you've got an SFP Plus system, the electronic dispersion compensation happens on the router itself, and so you're tied to the quality of whatever that box is for doing these long reach things. So a lot of people went out and bought a lot of SFP Plus systems back when they didn't have any long reach at all, and then found out that, oh, this particular device isn't actually good at working with, no matter what optic I put in there, isn't actually capable of doing the dispersion compensation. But dispersion is a much bigger issue at 40 and 100 gigs, so it plays a critical role in actually making these things possible optically. You got the 3 R's: reamplifying, reshaping, and retiming with repeaters. So 1 R is reamplifying. That's basically you're just taking the signal and you're making it brighter. So you get a very low signal, and you're now making it bright enough that the receiver can see it. A 2 R is reshaping. You're restoring the original pulse shape. So you need to actually be able to distinguish the pulse to see if it was a 1 or a 0. So you restore that shape, but you don't need to completely decode the thing. And then 3 R is retiming. You're actually readjusting the spacing of the pulses. At this point, you're usually just going optical to electrical and back to optical again to get the full 3 R regeneration. Sometimes you'll see eye diagrams out there. Basically, this is just an oscilloscope display of what is actually happening. So every time the signal crosses, it's a 1 or a 0, and this is kind of what it looks like after it's gone through a fiber with a lot of impairments, dispersion things. You end up with this big mess, and you can't tell what you've actually got. We talk about bit error rates. So what happens is, as you get impairments, as you get noise, distortion, dispersion, loss of signal, you don't just completely die. What happens is you just start taking errors. They might even not be noticeable at first. You might just have a very small % of packet loss, and then as it gets worse and worse and worse, you get more and more packet loss, and all of a sudden people start complaining. But the link is still up, still passing light, passing signal. Typically, you try to target for a bit error rate, which is better than 10 to the minus 12. But as you start to get down the end, you're literally 1 dB of loss will cause a 10-fold increase in errors. And then all of a sudden, you end up with a very, very errored link that if it's right on the edge, you might not even notice it at first, and then someone bends a cable, and all of a sudden it goes over the edge. So there's a bunch of tools of the trade when you're working with fiber. The first is the optical power meter, the light meter. It's just going to measure the brightness of the signal. Like I said, there's going to be, on most fiber meters, 2 modes. One which is absolute. It says, I have this much light, and that's going to be dBm. If it does not say dBm, you're in the wrong mode. The other is a relative mode. So when you're testing fiber, you might have a known light source that puts out X amount of signal. You go to the other end of it, and you're in dB mode, and you say, well, I've lost this much over the span. That's just for testing fiber. That's not for measuring how much am I actually putting out from my device. So you need to make sure that you're talking in the correct unit. Literally, if I had a nickel for every time someone told me they just measured 70 dB in my fiber because they're in the wrong mode, it happens all the time. So just want to point that out. Make sure you're in the correct mode. You've got an OTDR, an optical time domain reflectometer. What this does, it lets you characterize the fiber. It sends pulses of light down, and it looks for reflections. Every time you have a splice point or a connector or something that's not completely perfect, you're actually going to get reflected light back. You're gonna hit an edge, and something's going to bounce back, and you're actually going to be able to characterize this and see exactly how far out these things occur. So here's a little diagram showing what happens, like you can see the splice points, you can see the rate of loss over distance. So you'll typically see this used when you order a dark fiber, or when you're testing something and you want to know if the splices are good and the whole thing is engineered well. Now we get to a bunch of fun questions. Can I really blind myself by looking into the fiber? Beware of big scary lasers. Do not look into beam with remaining eye. I printed this up on a t-shirt and I wore it when I got my LASIK done. The doctor loved it. So lasers are grouped into 4 main classes for safety. Class 1 is completely harmless. There's nothing you can do short of poking yourself in the eye with it physically that can actually hurt you in any way. It's either low powered or you can't look at it. So for example, your DVD, your Blu-ray player has a high powered laser, but it's sealed in a box and you can't get at it when the thing's running. So it's a class 1. Class 2s are only harmful if you actually intentionally stare at them. You're crazy and you're like, I really want to hurt myself. So laser pointers, your common laser pointers are class 2s, things like that. It's actually bright enough to hurt you if you sat there and looked into it, but don't do that. Class 3 shouldn't be viewed directly. Class 3 is broken up into 2 different things. There's a new system and an old system that used to be called 3A and 3B. Now it's 3R and 3B. But basically the difference is whether you have a reflex to look away. So if it's a certain frequency of light that the human eye can't see, you don't have that reflex to, I'm not going to look at that. That typically gets you into a 3B system. And then class 4, burns, melts things, starts fires, destroys Alderon, anything in that category. So the lasers that we work with in networking are all in the infrared spectrum. The human eye stops seeing above about 600 nanometers, so even the 850, you're deep into infrared. There's actually 2 categories of infrared called near infrared and far infrared. The difference being what the eye will filter. Because your eye is not meant to see an infrared, it actually does a very good job. The cornea just blocks it. So the near infrared is actually worse because your eye doesn't do as good a job of blocking it. So the long distance stuff, the 1550 systems, your eye actually does a really good job of blocking that. It's what's called IRB. But the near infrared systems have a potential to get in. Basically, if you look at any router out there, there's not a single router out there that you can go to, pull a pluggable GBIC, XenPak, XFP, whatever, that is not a class 1 laser. These things put out power at most in the 1 to 2 milliwatt range. It does nothing. Optical amplifiers are where you start to cross into the point of actually putting out enough power that you could potentially damage your eye. So if you throw something into a very powerful amplifier, that's when you'll start to cross into the 3B range, or 3R or 3B. And the DWDM systems in general, if you take 40 channels and you put them all together on one fiber, you've now got a 40x signal. That can actually start to cross into the point that you actually care. So the question is, should I wear my goggles to the colo? Probably not. Generally speaking, everything that you're going to see on a router directly is going to be a class 1, just doesn't matter. Most of the time you don't see anything anyway, so there's not much point in looking at it, but you don't need to freak out over having dust caps on everything. It's not a real issue. Even on DWDM systems, as soon as the signal hits the air, you're not taking the fiber and holding it right up to your eye. You're going to start to lose signal rapidly. And like I said, anything above 1400 is going to fall into the IRB category, and the eye is going to filter it. So why even look into the fiber at all? You can't. You can't actually see the signal, so there's no real benefit to it. When you look at an 850 signal and you see red, what you're actually seeing is a sideband. You're seeing the very edge of red that's out of what you're actually trying to transmit, but the generator is not perfect. One cool trick is that digital cameras actually can see infrared. So here's a picture of a digital camera photographing a TV remote control. And you can very easily see the infrared signal. So you can take your phone, put it in camera mode, hold it up to the fiber, and see if you've got light on a bunch of different panels. It's a quick trick. Next question I get a lot is, can optical transceivers be damaged by overpowered transmitters? Yes and no. It's not actually the transmitter that does it. It turns out that all transmitters basically transmit about the same signal. the difference between a 10 kilometer and an 80 kilometer optic, the transmitter might only be 3 dB, and it might not even be that much. The way that long reach optics get better is they have more sensitive receivers. And that's the part that you actually care about damaging, not the overpowered transmitter. So there's two different thresholds out there. There's what's called the saturation point. It's the point where the signal is so bright that you just can't read it anymore, so you start taking errors. And then there's the point where you actually hit damage. These differ depending on the exact make of the optic. You can look it up, it's in the spec sheet. But generally speaking, only 80 kilometer stuff has this issue. So here's kind of a little diagram showing what the, you can't read this very clearly, but showing what the transmit and receive windows are. So you see that like a 10 kilometer optic, you can't do any of the above. Nothing that you send or receive is going to fall into damage or blindness threshold. With a 40 kilometer optic, you have the potential, if you take a 40 kilometer optic and you run it through 6 inches of fiber, you're going to be so bright that you can't decode the signal, but you're not actually going to damage anything. With an 80 kilometer optic, if you take two 80 kilometer optics back to back and you run it through 6 inches of fiber, you're crossing the point where you're actually causing damage to the optic. So that's where people say, plan this accordingly, use an attenuator, use something, don't just use any type of optic without worrying about it. Big question that I get asked a lot is, do I actually need to be concerned about bend radius? Yes, you do, because remember that fiber has to enter at a certain critical angle in order to propagate. One cool thing out there is you can actually check the signal on a fiber with a little clamp meter like this. You can actually just clamp it onto the fiber, and it'll bend it a certain way, and it can actually see the light leaking out through the cladding and through this. So you can get a light meter and see what's actually on there. It's called a macro bend. There are bend and sensitive fibers out there, but you won't see them in data center use because they're not as good for optical signal. So just don't tie your fiber up into knots. Big question I get asked a lot. Can you make these two transmitters on different wavelengths talk to each other? More or less, yes. Basically what happens is all optical receivers are wideband. So if you're in the laser category, you're going to be able to decode anything between 1260 to 1620 nanometers. You're not going to be able to make an LED or an SX850 talk to an LR, but you're going to be able to make a 1310 and a 1550 talk to each other, absolutely. Many D2B systems are actually built around this. You don't need two strands of fiber for transmit and receive. You can put them on two different frequencies on the same fiber and receive on anything. The only gotcha here is that when you use an optical power meter, it actually has to be calibrated to the frequency that you're using. So if you've got the power meter set to 1310 and you're expecting a 1310 signal and you get a 1550, it's going to be wrong by a few dB. So you need to know what you're doing to have the power meter work correctly, but otherwise it works perfectly well. Here's obscure optical networking trick. You don't actually need a pair of long-reach optics to get over the same distance. What happens is, say you want to go some good distance and you've got an LR and an ER. You've got a 1310 that does 10 kilometers and you've got a 1550 that does 40 kilometers. What happens is the 1550 signal will have lower attenuation because it's in the right frequency, and the 1310 signal will be landing on the optic that has a more sensitive receiver, and it'll just work. You'll probably be able to get 30 plus kilometers, maybe even 40, out of mismatching an LR and an ER. It works perfectly well. Obviously, plan your system, check your power plan if you're going to use this, but it works very well. Another common question is, do I really need to clean the fiber to have it work right? The reason you need to clean it is not typically for attenuation, it's for reflections. If you get dust or things in there, you'll cause reflections in a way that you won't necessarily see on a power meter, but that will disrupt your signal. So yes, cleaning fiber is good, and I threw in a link to lots of detailed documentation on that. Other miscellaneous fiber information, people want to know, how fast does the light actually travel in fiber? It's very simple to do the math on this. So the speed of light is about 300 million meters per second. and you can actually go look up the refractive index of the cores. So like an SMF-28 has a refractive index of 1.468. That means that light travels at, the speed of light divided by 1.468. It's about 200,000 kilometers per second. Do a little math. You can see that it's about 126 miles per millisecond. And remember that when you're doing a tracer route, you're actually looking at round trip time. So cut that in half again. About 100 kilometers per millisecond is what you're going to see based purely on distance. That's what's going to cause your latencies in ping and trace route. Why do I see a much higher value in real life? Remember, the fiber's never laid in a straight line. It's laid in rings. It's laid in ways that try to go to hit population centers or run through tons of patch panels. So there's always a lot of overhead. You'll in the long distance systems, you'll have dispersion compensation spools. So you're adding distance there. A little bit about the future of optical networking technology. Right now, most systems use what's called NRZ, non-return to zero. It's a very simple system, but there's actually more efficient modulations out there. Everything from duobinary to DPSK to DQPSK. You're starting to see QAM stuff being looked at. It doesn't really matter much outside of these technologies will let you be more spectrally efficient. So here's kind of a diagram showing that within the same 25 gigahertz signal. At NRZ, you might be able to send 11 gigs. At duobinary, you can now send 22. At DQPSK, you can now send 44. That's basically the basis of anything above 10 gig technology at this point. Optically, where we're at, 40 gig is the max. There's no optical 100 gig in any kind of practical sense. So to make 40 gig work and actually get good distance, you need to use techniques like this, and they're starting to become more and more common. Another concept that people talk about is alien wavelengths. So normally, when you run a DWDM system, it's run by one person. But what happens if I want to? So right now, if I go out and sell a wavelength, my customer doesn't know about the color. They don't know about the DWDM system. They get handed what's called a gray, uncolored end. But that means I'm now paying for conversion on both ends, as well as the optics to talk to the customer and the optics to talk to myself internally. What would happen if I could just go to the customer and say, hey, you get this frequency. You send your own colored light. That's called alien wavelengths. It has an advantage in cost, obviously. The disadvantage is if you're working with an amplified system, you need to know what is being transmitted into that, or customer will go out and re-plug something else in the wrong way, and it will screw up the amplification. But if you're just doing a very simple unamplified system, you can absolutely do this, and there's people starting to look at it as a product. And that's basically it. Questions, anybody?
What are some of the biggest challenges with deploying wave-division multiplexing in a production environment?
Biggest challenges with deploying WDM in a production environment. Mostly just a matter of, I'm trying to think what big challenges are. It's relatively simple when you know what you're doing. The big challenges are if you've got to amplify the system, you get into something that's very quickly very difficult to maintain. If you've got complex rings, OADM, things like that happening, it becomes a lot more complicated than just a simple point-to-point system. Most people can figure out a point-to-point system very quickly, and most of the time it actually works out very well. But when you start getting into OADMs, when you start getting into amplifying, maintaining the network correctly to do that, that's when it gets tricky. Yeah.
When you were talking about ranges, you said that you normally include a margin. What percentage of margin do you normally include?
A margin for just budget. It depends. You can go look up. There's all kinds of guides out there that kind of show you what you should plan for. I would typically, it entirely depends on the system. I would typically want to do something at least like 5 dB to deal with people in the cable trays. It happens all the time. You're a third-party colo, and you order a new cross connect, and they get up there and start running the cable, and they jostle it. And if you've ever graphed the transmit power, you can see when they do that, when they start bending fiber and things, you can see some variance. So you just have to keep that in mind and set a value that you're comfortable with. But there's lots of guides out there where you can figure out exactly how to do that to your goals. Yep.
So like ZR80K seems like they're pretty close to being mainstream. What's like roadmap for length coming up next?
To go beyond 80 kilometer. Basically nothing. So 80 kilometer is about the most that you get out of a single transmitter without doing something like amplifying. FEC is the technique that you use to get past 80 kilometer. But you're doing that with a software trick. So there's people that are making optics that integrate the FEC encoders and receivers actually in the optics, so your host box doesn't need to know about it. Other times there's vendors like Cisco and the ASR9 case makes a line card that will actually send a FEC signal. So that lets you take it from 80 kilometer to go to 120. But really what you hit is a point where there's only so much signal you can put down. If you send it any brighter, you get noise. Or you get something that's outside of the power spec of what you can actually do, especially with SFP+. You've got like a 1.5 milliwatt draw cap on these things. So there's only so much you can do past that point. You're never going to see a 200 kilometer, maybe you will, but you're not going to see it with anything other than techniques like FEC, things like that, yeah. Or just very improved receiver sensitivity or protocol stuff. So there's a lot of, I've seen 200 kilometer 1 gig optics because we're now at the point where 1 gig is so easy to work with that we can have very, very, very sensitive receivers that can decode that because it's not modulating nearly as fast. But things get exponentially harder as you get faster. So really what you're seeing right now, the future is figuring out how to send 40 and 100 gig signals over long distance so that 100 gig becomes something more than a fancy cable management solution. Yeah.
What's the advantage of the Raman amplification? Is it really for ultra low?
It's a different type of amplification. So typically you'll see that on undersea systems. Different frequencies of light use a different type of amplifier. That's really the difference. It's not a different technique or anything like that significantly.
What was that question?
Oh, Raman amplification. Anybody else? Yeah.
You were talking at the start of the presentation a little bit about multimode fiber. I was wondering, how does it stack up compared to like twin-ax cable these days? It seems to be becoming more and more popular.
Not my area of expertise, but what people are working with on multimodal right now is doing LRM is very popular. So if you want to get any type of distance in the 200, 300 meter range, you're still going to need some type of fiber. But LRM is a very enterprise solution. The interesting thing is that single mode is actually cheaper to manufacture than multimode. So what you're doing is, to be cheap, is not in the fiber, it's in the optics, it's in the components. These days, the cost of LR for SFP Plus is so cheap that most people in large production environments say it's a lot easier to standardize on single mode everywhere than it is to try and save $20 by doing some LR and some SR. Anybody else? Yeah.
Can you comment on ALS? Do you like it as a feature? Do you think
On what?
ALS, automatic laser shutdown?
Not something I'm super familiar with, but there's a lot of safety techniques out there, and that's one for if you've got a fiber cut, you don't want a extremely powerful amplified signal going out, and so systems will detect a cut and turn off the laser. It's a good safety feature, but it's not something that you'll typically encounter outside of a very commercial, a long haul type system. You're not going to see this on any routers or anything like that. Yeah. Yep.
You mentioned the 10 gig and higher will channel on us to like 2.5.
Yep.
Does that have an effect where it's channelizing your data? Like, I don't know how it's splitting it and then bringing it back together. Does that mean that you can only bond to one channel, and so your throughput for any one particular packet would be the 2.5 channel?
Nope. So it's not like load balancing at layer 2 or layer 3. It's completely layer 1. It happens at the bit level. Where you see these systems used, so getting into 10 gig, certainly if you wanted to do anything over multi-mode at the time before LRM came out, you definitely needed something like LX4. You needed to not be doing a 10 gig signal, but to be doing 4 2.5 gig signals. The same thing at 100 gig, you need to be doing a 25 gig signal because an actual 100 gig modulation is just too difficult right now to do commercially. But no, it doesn't channelize it in any way. It just does it purely at an optical layer. So looking back at the LX4, for example, between your router and your Zen pack, it actually happens over 4 data channels already anyways. When you move to XFP and XFP Plus, that was the first time that it actually moved into happening at a pure 10 gig signaling. So this type of stuff happens on the interconnection between components on the circuit boards all the time already anyways. And in that case, it actually made it easier because you didn't need the serializer. You didn't need the SerDes. Anybody else? All right. Well, thank you very much.